specifically starting today our discussion of mobility. We had seen a brief glimpse of this within the closing moments of the last session, and we're going to look at a little bit more detail on how this mobility is achieved within today's lecture, particularly highlighting two different types of mobility that we noted during the last lecture. Can anyone remember the two different types of spatial landscapes that are provided by AnyLogic? I delineated two types of landscapes that AnyLogic supports, two types of sort of spatial context. Does anyone remember the distinctions between them? Okay, discrete and continuous is the key distinction. Where the continuous landscape essentially assumes that each individual within that landscape is a point that's essentially a virtual zero size compared to the scope of the landscape. And so different agents can pass each other, and they move in a continuous fashion. That is, they move over space in a fashion that's more or less continuous. It doesn't go in leaps and jerks unless you explicitly request that. So it can occur in sort of a smooth way, transitioning from one point to the other. For a continuous environment, what we're doing is we're associating with the agent with a certain direction and a certain speed, and they move in that direction and speed in a continuous fashion until they reach the destination. And when they reach the destination, what happens? Does anyone remember? I described it once or twice, sort of in passing. When they reach the destination, what happens of significance? Well, an event is triggered. An event that could be used to trigger a transition in a state chart. For example, now you've arrived, you've arrived at the lake, and therefore it's time to drink water if you're a deer. You've arrived at a food source if you're an elephant, and it's time to eat. Actually, that model doesn't have that in there, but it can be. It's the source of an event. Yes, Dawn. So we're going to go and I'm going to set this up so that our remote partners will hopefully be able to see this. But we'll go over to AnyLogic, and we will go to, okay, I thought I had AnyLogic up here. Give me a moment. There it is. Yeah. So if we go and we look at a state chart within AnyLogic, so let's suppose the model with which we were working last time, and we were to take a look at the state chart associated, this would have to be the model with a state chart, so the minimalist network ABM model that we built last time, that we were using last time. If we go to that model, what we'll see is that, here we go, what we'll see is that this is not the version I expected with a state chart. I'll just have to demonstrate it in another one here. Say the SAR agent-based model, which we've worked with extensively. If you were to go here, what you'd see is that associated with each transition is a set of options regarding under what conditions that transition is triggered. The transition itself is instantaneous, but there may be some amount of time that transpires that you spend in this state, in this case the infectious state, before going on to the recovered state. And that amount of time is dictated by the triggering of this event. The event is triggered by one of several eventualities, and you have your choice as to what it's triggered by. The main ones which we've emphasized are what? Who can tell me some of the major events that trigger transitions? What are the types of events that trigger a transition? Give me at least one. A timeout, yeah. What's another one? Oh, sorry? A rate. And that we analogize that to the first order delays we saw within Benson. It's a chance per unit time, right? So again, if it was a rate of 10, you'd have an average time of 0.1 within that state. What were some other transition types? Sorry? A message. That was used for communicating between agents. For example, one agent infecting another. There was also a condition transition we didn't talk much about, but under an event that, under the situation that a certain condition is true, it goes between these two stocks, these two states. For example, if a stock reaches a certain threshold value, it might trigger this transition. I mention a stock particularly because any logic keeps track of the value in a stock in a fine enough grained way and notifies the agent when it's changed so that it could trigger the transition. In general, you might have to call unchanged on that agent. But another one of these options is agent arrival. Okay, this deals with Dylan's direct question. So, how do you trigger something based on agent arrival? This is one of the key nexi, okay, the key points where you can catch arrival of an agent and have them therefore change their state and thereby their behavior. Okay, that's one of the transitions, or one of the points, but it's not the only one. If we want to go see another one, and really this is the only other major one of which I'm familiar programmatically, or excuse me, in terms of the UI. If we go to person here and we go to agent, okay, I thought it was actually right there that there was yet another place for it to have an on arrival event associated with the agent, but perhaps it's only, there we go, yeah. So it's only when they're in a continuous 2D. So did folks see that? So this originally had no on arrival for discrete 2D. Okay, so question here, yes. So from Neil, yes, can't see any logic. Okay, it's showing that it should be being displayed, but I'm going to switch over to the to try it again. So here we go, and there we go. Okay, so I was sharing the desktop there. It should have been displayed according to how it showed it, but okay, hopefully it will show on there. So fundamentally, if you had this transition, you could catch this with agent arrival using the transition. Alternatively, if you went to person and you went to the agent properties of person, you could go and catch the arrival event, but only in the condition that the agent is moving in a continuous 2D space. So if the space type is a continuous 2D space, there's an on arrival handler here. By handler, I mean that whatever code I place within this on arrival handler here, this on arrival bit of text here, will be executed when the agent arrives at its destination. This is also true for agent 3D, but it's not true for discrete 2D agents. So the key point is that those are the two main places you'd go to handle arrival by an agent. On the one hand, for transitions, where you can treat it as an event that triggers a transition, and secondly, under the agent properties, the agent tab of the properties menu for the agent itself. Okay, those are the two key places. There is actually, I believe, a third one, but it's not enabled by the interface, and that is you could actually create a method called onArrival and then handle it when that method gets called. It gets called at the point of arrival, and that can also handle it programmatically. Okay, so that was just a little bit about continuous environments. As a review, the other sort of environment is what? There's continuous and then there's discrete. And a discrete environment is distinguished by that. We saw an example of a discrete environment being, for example, predator-prey agent-based. And in what way is a discrete environment distinguished from a continuous environment? Remind me. There's two major ways I emphasize. If by my emphasis just now on continuous environment, you might be able to guess it. So, in what way is a discrete environment distinguished? Discrete environment is distinguished by two things. Number one, it's distinguished by the nature of the movement, whereas movement within a continuous environment goes on more or less autonomously. You say, move in this speed in this direction, and you just go, and you're woken up when you arrive. In a discrete environment, you just say, jump to this space, go to here, go to there. Now, what is the space you jump to? It's a cell. It's a cell. It's a particularly discrete unit of space into which all of space is divided into a set of these cells, such that they're mutually exclusive and collectively exhaustive. So you go to a particular cell, and you're jumping around in that sense. The other major distinction is what? This is true. This is actually true. So that's nice. That's a third distinction that I wasn't emphasizing here. Okay. I say this is true with a caveat. You actually can have steps in a continuous environment. You actually can have steps triggered. It's a lot more typical within a discrete environment, where you have them updating all in lockstep, one by one, across the entire space. So that's an important aspect of it. Often we want these cells to all update together, collect all the information they need to update before performing any one update, and then update having collected all the information they need so that you don't have to worry about which one went first. It's independent of that. It's invariant of whichever one goes first because they already have all the information they need. And that finishes that step. So that is an aspect that's frequently paired with discrete things, but there's a more basic property of the way any logic describes these discrete cells. There's a property of these cells that's important that we talked about last time. Does anyone remember what it is? Sorry? Okay, the time one is just related to what Dylan said, that you have often these things are just programmed to update in a series of steps. And so that frequently comes along with it. But actually it has to do with the occupancy of a cell. A cell can only be occupied by 0 or 1 agents. It can't be occupied by more than one agent. There's mutual exclusion. The assumption is that when a cell is occupied by an agent, it's full. It's full, at least for that agent category. I'd actually have to go check if you could do it for two different sorts of agents, so you could have you and your dog in one cell simultaneously, or if it can only be you or your dog. But the point is that there's an occupancy limit that's enforced. That's important because sometimes you can get bugs where two agents want to go to the same cell and they appear there. That one appears first, the other as an error because it's trying to go there. Okay, so we saw predator-prey agent based. So if I were to go look at this, we saw two examples of things with cells last time. For example, we saw the game of life where we had these cells. And here we didn't have any movement per se. That's why I covered it last time. We had spatial embedding within these cells, but there was no movement. A cell could be alive or dead, but it didn't move per se across the landscape. We're going to be looking at additional ones where there is movement across the landscape, but one I think you've seen before is predator-prey agent-based. I don't think we looked at it last time, but we've looked at it in some previous session. And for predator-prey agent-based, which is again one of the example models, here you have actual movements of lynx and hares across a landscape. But this is a discrete landscape. It's a landscape where the landscape is divided into a set of cells, and each cell can support a hare or lynx, etc. And this is a summary of sort of the number of lynx and the number of hares. For those who are interested, there's actually a very nice set of differential equations called the Laca-Volterra equations, which describe, in using nonlinear differential equations, two equations, one for lynx, one for hares, two stocks. They describe the cyclic behavior too. And it characterizes the fact that there's many lynx around, many hares around, the lynx can eat more and therefore multiply more, have more kits, I think they're called. And yet if there's too many rabbits or hares around, they won't be able to find enough food, so rabbit population growth will be slowed, and their death rate may go up, etc. So it's a set of differential equations, which we won't be covering in this course for that. But these are two examples of discrete systems. So I'd like to talk today some about how mobility is captured within these models. So we're going to be talking about agent mobility in 2D landscapes. Okay. So I'm going to switch remote folks over to the presentations here, and we'll get started on the slides. Okay. Here we go. Okay. So the focus of today's discussion will predominantly be on mobility. So thus far we've looked at spatial dynamics where agents remain stationary, continuous space or discrete space, and now we're going to be looking at mobility. And I've talked about these sort of characteristics of each thing. Importantly, for discrete, we have this notion of columns and rows that goes beyond the notion of spatial extent that we have in both continuous embedding. So within the discrete case, we have extra parameters associated with columns and rows for the space. That's distinct from the issue of how wide is the space in a spatial sense. It's how many cells do we have in each, how many cells are there, widths are there in each dimension. Okay. This says agent move continuously, but I don't think that's true. It's agents move discontinuously. Okay, so let's talk about some of the methods we use for this. So in continuous space, when we request information from or changes to an agent in continuous space, we're calling some methods like move to, which can actually move an agent in a discontinuous fashion, but more commonly we'd set their velocity, and then we would, okay, I don't see it, it should be there, set target, the move to, excuse me, the jump to, this one here is what moves an agent to a location in a discontinuous fashion. So discontinuous, okay? By contrast, move to initiates agent movement towards location. This should really say towards location. Okay, so they start moving towards the location, and they're moving with the velocity that's been set by you or the default velocity. We can also set their initial location in the space using a separate primitive set x, y, and we can set their rotation so that their icon associated with them appears in a different form. In other words, their presentation that we add to the agent will simply be rotated around. Okay. And then we can ask for some information like what's their X and Y position, are they moving, what's their current target towards which they're heading, and what's their current rotation. Okay. So this is information that can allow us to elicit information on particular, to secure information related to a particular agent within the model. Information we may have set earlier, but have now not saved away, such as their target and their rotation and their whether or not they're moving. Okay, so let's illustrate this. I'd like to create a project that illustrates the basics of this that's crudely called movement towards mouse. You can kind of guess what this does. So this is going to be a very, very simplistic one. I have to apologize. I'd like something a little bit more creative than this. I would, for those who are looking for more of a challenge, I would suggest in the time we're building this, you might want to create something where the agents exhibit Brownian motion and they kind of jiggle around in space, or where they go to random places. Well, oh man, maybe we should. Who wants to do movement towards mouse? Who wants to try something a little bit more interesting? Okay, let's. Oh man, I like putting myself out on a limb, don't I? Okay, let's. Ladies and gentlemen, let us compute. So let's go rehearse. Go through the steps here. Okay, let's add a new model. And we'll call it. Simple mobility. Okay. Simple mobility. Okay. Oh yes. Thank you. Can't see. Okay. Yep. I'm switching back to AnyLogic. So, let's try this again. Okay. So, switching over to AnyLogic. Boom. There we go. So it should appear on your screen here. So all I did in AnyLogic thus far was to do File, New, Model, and I called it Simple Mobility. Okay. By the looks of it, this should be displayed for you. Neil, could you confirm when you see the screen there? So it's called Simple Mobility Model, and I'd say start creating a model from scratch. Okay. So it's creating the model, boom, 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 and here we are down here. Let's go rehearse the steps. So what do I need to do to add an agent? We're going to add an agent here. It's going to be an agent population. What do I need to do to it? Please, someone? What do I need to do to add an agent? Yeah. I have to add an active object. Okay, good. Okay, so active object class, and I have to add person. Okay, person. Boom. Okay, why isn't that person? Is that person currently an agent? Yes or no? No. Okay, Neil, can you see the screen at all? Let me know. Okay, so how do I turn it into an agent? Yeah, I have to go to property general, turn it into an agent. Okay, now it's an agent. But we have to lend them some representation. Let's go lend them a representation. But I want to lend them a very particular type of representation. Not just a standard circle will do. I want to give them a representation that's anisotropic. I want to give them a representation where I can tell what their rotation is. Oh man, I was going to give them a square because that reflects my square personality. But let's give them something a little bit more interesting than that. Well, okay, so you put me up to this. Which icon do you want to have? You want to make them a forklift truck? Or perhaps a lorry? Okay, let's, what do you think? Okay, should we make them not a USA map? I don't think we'll do that, but let's make them a patient. Say, okay, so we'll keep them as a patient, and maybe we'll draw them, we'll enlarge them as a patient. Okay. Okay, so here's here's our patient. Okay, so what I'd like to do now is to add a population of these agents. How do I do that? Where do I go? What's that? Where do I go to add a population of agents? Okay, main. Yeah, I go to main. And what do I do to add it? Add it? Folks, come on. Okay, thank you. Yes, and let's make it population. Okay, so let's set the population size to be 100. Well, to be 10 initially. We don't want to have an overcrowded Brownian motion. How do we do this? Actually, we won't Brownian this. How do we set a population to 100? Yeah. Okay. Thank you. I can't be the only one doing work here. 10. Okay. Okay. So, what do we have to do? So if we run this model right now, what will happen? Okay, will we have a population of 10? Yes. We'll have a population 10. Where will they be? We've created a singularly boring model, because where's the population? Can anyone spot it for me? Where is it? Well, okay, they're all up here. There's no environment to lend them location. That's exactly it. Here they are. There they are. They're all of them up there. They're singularly sort of singularly homogeneous. Okay, so how are we going to lend them location? We have to add a what? Environment. Okay, Neil, are you able to see this thing still? Okay, so let's go add an environment. We have to go up to the main thing. We have to go add it in. We're adding it to main, right? Yeah. Okay, so I want to make them go and let's make a continuous one. Okay. Continuous environment, okay? And okay, this could get pretty interesting, actually. Okay, so it's a continuous environment, and we're going to set its properties. Where do we go to set its properties for the environment? Its width and stuff. We go to advanced. Thank you. Okay, so it's width 500 by 500. Fine. Okay, layout type, all that. That's good. Okay, if I run this now, will they appear any different? Do you think? How many people think they'll appear different than before? Different? How about the same? Okay, they appear the same. What do we have to do? I mean, this is a good rehearsal for debugging some basic things from any logic. What do we have to do to make them appear at different locations? We have to tell them about their environment. Why? Because different populations might have different environments associated with them, for example. For example, one population might be associated with city 1, another population with city 2. And because of that flexibility, you got to do more work. There ain't no such thing as a free lunch. So you got to go to the population, go to the general tab under environment, and give the name of the environment. Okay? So population environment. Are people following along here? Does anyone need me to go back to a step? Okay. One of the reasons I'm actually open to doing this is because I've been told that this sort of rehearsal is sometimes good for people to kind of come back to the issue. Okay, so now we have our people and they're located at diverse points in space. And we could lend them different colors by having it randomly pick a color, for example, right? That's all fine and good if we wanted to. Okay, now, ladies and gentlemen, I want you to again tell me some things here. So I want to set each of these folks in motion to go to a random place in space. Starts out. And when they arrive at that place, I want them to go towards a different randomly chosen place. How do we do that? do we do that? Good, good. That would make a lot of sense. Now, I'm a software engineer, and one of the things I'm thinking forward to here is, I haven't done this exercise before. It's a nice little exercise, I suppose. But one of the things we're going to have to use is we're going to have to randomly pick a space given the width of the space. And we're going to need to somehow get the population, or sorry, the environment width, sort of the width of the population. Now, either one of you, could you folks tell me, can the environment give its spatial extent, its width and height? I believe so. I think it's get width and get height. I just don't have to remember. Okay, so let's take up Dylan's suggestion. We're going to go to population, and we will go add in a state chart. So add in a state chart entry point, and this will be, I don't know, mobility, something like that. It'll be the mobility state chart as distinguished from their infection progression state chart or what have you. And now let's add in a state that will be called traveling or something like that, right? And when we enter this state, we're going to go towards some randomly chosen place. Okay? So what would we do here? How would we go towards a randomly chosen place? Move to, yeah. So this dot move to, right, because I've got to move myself. This dot move to, and I'm going to go to some randomly chosen place. So I'm going to go to a randomly, uniformly, with uniform probability over the space, okay? So how do I do uniform in a continuous variable in any logic? How do I draw a number from a uniform distribution between 0 and some number I call uniform? Okay. Uniform, okay. Uniform, and I have to go between 0 and what? Well, the width of the space. This dot get main dot environment dot get width. Oops, width. Okay, so let me just drag this over so we could have more screen real estate here. Okay. Now, personally, I've really mixed aesthetics on this. So that's one, and then we want to go between 0 and get what. Now, note we're assuming here that it's 0 based, but it is all relative to its original place. So what is this doing? This is saying, okay, move me to a certain place. What is that place? Well, its x location is going to be given by this draw from the uniform distribution between, in the uniform distribution, this call takes a single parameter, a single argument as we call it, single value. Specifically, it takes the value, it needs to draw between 0 and whatever value you want to draw it. For the first of these, it'll be the value of get width. So we're going to draw something with uniform probability between 0 and anywhere in that space, and the end of that space. So it'll be anywhere in that space, and then similarly get height. This is the latter one here. Now just for aesthetics, I'm going to divide this up into 2 lines, so it'll be something like that, and then we'll kind of see. Okay, it's get width and get height. Okay, so what should happen now? Let's try to build this, and it's a happy camper. So what do you think would happen if we try to run this now? Let's run it now. What's going to happen, folks? Who can tell me? Ooh. Sure. So, so this is the code. Here, there's the code for the entry action of this state, and it's this dot move to. And you got to be really careful here with parentheses, and there needs to be a semicolon. So it's this dot move to, and part of me aesthetically has mixed feelings about this because it gets kind of overwhelming to look at, and I'm tempted to instead do something like double x equals, or x dest for destination, and then double y dest for destination dot get height, so that it's clear. It kind of is self-documenting that the first of them is the x location, the second of them is the y location. This would be another way to do it that has a certain self-documenting character to it. Does that make sense? Do you want me to look over it? Yeah, it's because there's a, that should be a, instead of a semicolon, just another comma. Oh, a syntax or until. It means you have yes, probably too many parentheses, but that doesn't look like too many. I would break it up this way. Do this x dest and y dest thing. One Yi, could you work with Molly on that? And who else needs help trying to get this going? Okay, so what happened there? Did it work? Did that work? Have we? Okay, so did people move? Okay, and if we ran this long enough, what would happen? There you go. All right, kind of like pick up sticks. Maybe your generation is too young to remember pick up sticks. But anyway, let's now complete the circuit. So how are we going to have these folks now, when they reach their destination, start up again? What do we have to do to go to a different place? What do we have to do? Okay. So how do we make them do that action again when they arrive? Good. So you notice I put that code. This was actually the key question. I should have asked you that. I robbed you folks of an educational learning opportunity. I put that code in the entry action, and I did that artfully because I knew that it would also be triggered by a return transition here. That code could have gone in this thing here, but then we'd have to duplicate it. It could have gone in this sort of initial state, but then we'd have to duplicate the code down here. Instead, I'm going to have this be triggered by agent arrival. And do I have to do any work when they arrive extra? Molly, did you get that? Yeah. Okay. Missing semicolon? Sorry. Yeah, sorry. Parentheses, yes. Yeah. Okay, just wait to see the last code. Okay, so now what I did is I had a transition back. And so what should happen now? Okay. Boom, boom. Oop. No, that's interesting. Okay, so it actually that is not what I expected to happen, actually. I'm gonna try. Okay, that's very interesting. What just happened? because I would have expected this entry action to be triggered yet again, but it's not being triggered right now. As the debugging thing, what I'm going to do is, why isn't that triggered? That's the interesting question. I'm going to associate it with this specific transition. The question in my mind is the transition firing or not? And I'm wondering if it's not invoking the entry action again. But okay, it's okay. Here we go. Boom. Okay, yeah, they exhibit different behavior now. Okay. Okay, that's more similar to what we wanted. Looks to me like they don't re-execute the entry action, which I thought they did when it just triggered this way. But it looks like the entry action is not invoked again. Okay, so that's too bad. So what I'm going to do is I'm going to associate this code with this entry point up here then instead, and then I'll have a separate code there. Now what should I really do, folks, there? For those from software engineering background, what I've done should be an abomination. You should be tempted to throw me out of this room. What have I just done that's really bad? I've just done something really bad. I've cut and pasted code. What should this be? Folks, what should this be? This should be abstracted. If I'm pasting code a bunch of different places, just crying out. Those from software engineer background should be able to almost hear the cries. It's crying out to be replaced by something that puts it in one place. You just call that thing. And that thing, ladies and gentlemen, is called a what? Function. Thank you. It's called a function. So let's go up and add a function. I add a function in from here, and it's called, what should we call it? Head to random destination. Okay? Okay, head to random destination. And we're going to just paste that code into its body of that function. And then instead of pasting the code at two places, we're going to just call that function. Okay? Okay, so we're going to call head to random destination from this entry point, and then we'll call it also from this this point here, from this little bit here. Okay, so now what we do is we've abstracted the details of that, all the details of how it picks the point to which to go, and etc. It just picks it there, and so now we speed it up. Oop, oop, oop. Okay, so let's try this again. Boom. Okay. Okay, so there. Oh gosh. Excuse me. Okay, that's okay. So I had them pick it there, and then I had it pick it here on agent arrival. I don't know what happened. That's weird. I thought I inserted it there already. Okay. So in short, ladies and gentlemen, at this entry and at that transition on agent arrival, it picks a new destination and puts them around. Okay, so that's kind of interesting. They're kind of mixing. Now, we can make this more interesting. So one thing we could do is we could have them actually periodically trying to head towards the nearest person or something like that. That would be kind of interesting. And in fact, we could do that quite readily. So we can have it so that they find the nearest person. This is something that's supported by Agent, I believe. So you could say, find the nearest person to me, for example, and then you could chase that person. Try to go towards that person. But I think I'll leave that right now. So this is just an example of mobility. What if we wanted to associate these people with different speeds? How would we do that? How do we associate them with different speeds? How if we wanted each person to travel at their characteristic speed? Yeah, you have a parameter for each one. Okay, so let's drag a parameter in. So we'll drag a parameter in, and it will be called speed. Okay. So we just drag that, and we're going to call it speed. What sort of type is it? How about someone not from computer science background? What sort of type is this? What sort of type of data is stored there if we want to keep track of their speed? Are we storing a string? Someone not from computer science background, tell me, please. It's a double. It's a double. Yeah, it's like a real value. Okay, so that's their speed, and maybe we'll give it a default value if nothing is specified. For example, if we create an agent without specifying it, that would be their default speed, 10. Well, it's 10 of these units, of these squares per time unit. Yeah. Okay. So, excuse me, I have to be careful about that. No, excuse me, it's 10 of these little things. So each of those squares is 10. Okay? So that would be a very slow speed. One might describe it as stately. And, okay, now we want to have this population be heterogeneous with respect to speed. How do we make them have different speeds, ladies and gentlemen? Where do I go? Where? Where? Where do I go to give them different speeds? Well, okay, we're going to have to use that. Okay, so maybe I'll come back to that. But how am I going to give this population, the people in this population, different speeds? Okay, go to population. It's a characteristic of the population. After all, some cities might have faster people, some cities might have slower people. That doesn't sound too plausible, but some climates might have faster people because there's ice, or because there's, no ice, and some have slower. Okay, so we got a population. Here's the speed, and let's give people a variety of speeds. Let's draw it from, after all, it has to be negative. Let's draw it from a log normal distribution with log mean, say, 3, log standard deviation, let's say 4, and I think there's a minimum value it specifies, which in this case I'm not really going to need. Okay, so I'm drawing their speed from a log normal distribution. What does that mean again? This is good rehearsal. What does this mean, that associated with this population, I specify the speed like this? What is that? What's the intuition behind what that means? Okay, so I have a log normal. Does that mean everyone's going to have a single speed? No. This is going to be run for each person in the population as it's creating them. It's going to run this. It's going to pick a value, draw a value from the log normal, draw a value from just going to run whatever's here. It's going to run it for each person to get the speed for that person. Okay, so we've given them a thing called speed, but does it, if I run this, will they have different speeds right now? No, because it doesn't know. There's just a parameter called speed. It doesn't do anything yet. How do I make it set their speed? Okay. I could put in a function, but it's actually a natural place for it. How would I have it set their speeds, folks? Well, really, just up here when they're about to head in, I could have it do what? This dot what? Set velocity. I think it's called velocity. Okay, boom. Okay, set velocity. So when they come into the state, at first it set the velocity. I don't think it has to be set every time. I think they'll retain that velocity as long as I don't set it again. Okay, this dot set velocity, whatever speed is. Okay, now let's, ladies and gentlemen, we're gonna go see this. Woo. Okay. How about these folks here? Are they? What's going on with them? Well, slowly you see them shimmy their way across the floor, shilly-shallying. They're just much slower than others. And in fact, if we were to go down into the population, we see some people are speed demons, possessing a high velocity, and others are slow evolvers. Others are somewhere in between. Okay, so now we've seen some elements. We could change the rotation so they fling around, etc. And again, we can ask things like, what's the nearest person to me? So there are, within any logic, and I wish I had the control space here, I could show it to you much sooner, but if you go up within any logic and you search, if you want to find the nearest person, you could go to agent continuous 2D, and you could have get nearest agent or move to nearest agent. See this, move to nearest agent, get nearest agent, to get information about who's around you, who's the nearest person nearby. For example, one thing we could do would be to periodically, this would be an interesting thing. I wouldn't suggest doing this, but I'm just kind of curious what will happen. So suppose I were to put in now a new transition here that is going to route this person. Periodically, they'll try to find the nearest person and head towards them. Okay. So with timeout, well, say with a rate of 1. So every time unit on average, they'll head towards the nearest person. Okay. So how would I do that? If this is the function here, move to nearest agent, how would I do that? Have them in vector. Well, I could just say this dot move to nearest agent, and I could give it the list of all agents, right? This dot get under bar main dot population. I think that should work. It may complain a bit, but yeah, no, it works. So now if we were to do this, I'm not suggesting you all do that, but if you were to do that, now you should, whoa. Okay, that's interesting. It's not immediately obvious that they're, I see. Periodically they're waking up and going to the nearest one, I guess. Okay, they're heading. Okay. Okay, these ones have sort of coalesced into a cluster because they're heading towards each other. you have nucleation sites where they're going at relatively small speeds, so they wake up periodically and they head towards each other, and oh look, there's some mixing exhibited between clusters. Well, okay, maybe my mirth exceeds yours, but this exhibits interesting spatial dynamics. And meanwhile, you have these folks. Why are these folks who are traveling around and exhibiting ballistic rates of speed? Why are they not clustering near these folks? Can anyone tell me? Why are they zipping all around and kind of with spatial abandon? Well, they're going really, really fast, and so they actually travel a very large distance in terms of sort of how far they travel compared to sort of how frequently they check. where someone is. So they keep on changing their partners, who they're heading to, I think, essentially. And then they get there, and then they update again, etc. So they're actually probably reaching people, but then just heading off in different directions, chosen randomly. But here we have a genuine case of clustering. These folks are exhibiting clustering behavior. Okay. Anyway, that was a bit of a side distraction. But the point is, the environment and AnyLogic does allow you to inquire about things like who's the nearest agent. So if you wanted to have collisions between your objects, you could actually do that by asking who's the nearest one around and seeing how far they are to you, etc. So I'm gonna get rid of this one. Okay. So mobility. Okay, so let's continue to talk here now. So now I'm going to go back, Neil, to the slides. So Neil, were you able to see that AnyLogic there? Hello? Okay. Start sharing. Okay. Here we go. PowerPoint. Boom. Okay. Okay. So here we are. Well, in retrospect, how many would prefer to do that exercise we just did rather than move to mouse? Okay. Okay. Maybe the experiment was a grand success. Okay. So you could follow move to mouse along as you see fit. Okay, so let's load in the model wandering elephants. Okay, wandering elephants was a model we saw last time, which is part of the the built-in model. So to open it, what you have to do is go to Help, Example Models. Examples, and I'm trying to remember if it's directly in this list here. There it is, wandering elephants. It's directly in the top level list, so you should be able to load it in directly. Okay, so wandering elephants is again an example of a model which where you have well, is it discrete or continuous? Can anyone tell me? I'm going to show it to you. Is that continuous or discrete? Does it look continuous or discrete? Is that discrete or continuous space? What might lead you to think this is continuous? What? Why might you think? Yeah? Okay, they never stop moving. Yeah, that's true. And they move in a what? In a fairly continuous fashion, right? What might make you think that it's discrete? All the way? Okay, yeah, but that could be. Right, okay, yeah, so they could be updating all together or something. In this case, they actually do use steps within this model, so it's not a bad guess. The thing that I thought might make you think that it's discrete is that you have these kind of grid lines here. Now it turns out that's imposed on top of it. That's not taking advantage of AnyLogic's properties. Let's just go see how this model is put together quickly. So if we go to wandering elephants, we go to the environment, and we could see it's a continuous environment, in fact, of space 500 by 500. And then there's actually a variable within main called vegetation that's, what is this? If folks, if you see that, what does that tell you? This is what? It's a double begin bracket, end bracket, begin bracket, end bracket. It's a what? It's an array. It's what sort of array? It's a 2D array because you have two of these sort of pairs of brackets. And how big is the array? This allocates the array new double 100 by 100, right? Okay, good. Okay, so here what we have is these elephants have an admirably succinct description of their behavior. So they're in a free wandering state for much of the time, and periodically they get a new direction. Every 12 time units they get a new direction, they head in a random direction. Okay? And then periodically their free wandering is broken by a physiological need to get water. So they got thirsty, and then they go to the water and they drink the water and then they return. Okay. Okay, so periodically there's this, well, this heading random is called every 12 time units, and it sets the agent speed. It obtains a random direction in which the elephant should be traveling, and it moves to a destination that's based on its current destination plus some displacement 1,000 times the cosine of the direction and the sine of the direction for y. In other words, it heads towards that direction. But this distance is large enough, 1,000, that probably it will never reach its destination. It just goes in that direction until it wakes up again after 12 time units, or it gets thirsty. Okay, and they actually go through and they define a custom distribution. This is something worth knowing about in any logic. They define a custom distribution based on a table. So there's this angle table. And basically any logic allows you to specify a histogram that can then be used as the basis for drawing a random number. Okay, so let me go over, you'll notice this stuff is to the left here. Take a look at angle table, for example. This is called a table function, and it's a function of values, function from one set of values to another, from a domain to a range. And this can then be used as the basis for random number generation. It'll draw it from this custom distribution. So you're more likely to be going to a moderately short distance or a long distance, somewhat less likely to be going in between. And similarly, there's a displacement table as to, I guess, how, that's kind of curious, maybe how far you're being asked to go. Although I thought it was always 1,000 here. I'm not sure they, yes, there's a thing called displacement that, this is actually for the speed. They're using it for the speed, or they're setting the speed so you go that distance within 12 time units. That's what it is. So you'll notice this comment here, new velocity, note that 12 is the length of time until it stop moving in this direction. Okay, so anyway, that's a little bit of an interesting thing. And then they have some code that helps them handle looking for water. So when they get thirsty, they need to slake their thirst, and in order to slake their thirst, they're going to go in a direction to find water, and it may be called here in the state itself, it calls heading to water. And there's this kind of code that kind of looks around. It says, where do I spy some water? It actually searches out from different angles and different distances, where is there water, and basically it finds some water and heads in that direction. This is situation one. This code is poor style, very poor style. It should be broken up. This is, some of you have heard me rant even upon this very code, I think. It exhibits poor style in a lot of different ways. Hard coding numbers here, like 0 and 100. The 750 is divided by 16 up there. But other ways as well. Like this whole thing here, if this dot get main dot altitudes CR is less than 0. What that's doing is it's testing if the altitude is below 0. In other words, is it water? Okay, and really you should have a method that says like is water, and it hides the details of this. I mean, this is really poor stuff, and I feel bad showing it to you. But then once they found water, they go off at a velocity and they move in that direction. Okay. Now, oddly enough, this model was built, I think, for an earlier version of AnyLogic, so there wasn't an on-arrival handler, and so there's nothing in that on-arrival. But you can also have state charts that depend on that. You'll notice that what they do is when they arrive actually at water, there's a message sent. The message is drink, and that's how they actually trigger the elephant to drink here. In this version of AnyLogic, you could actually have it directly sort of handle the on arrival. And then there's some periodic, and again this is partly because it came from an earlier version of AnyLogic. Within the agent, there's an on-step event where periodically it wakes up and says, where am I? Where's my current location in terms of a grid of vegetation? And it says, am I at a place with water? If so, I send myself a message called drink. This code is much more crufty than it needs to be. We could do this much more easily with on arrival. You just head towards the water. When you get there, you drink. I guess the one exception to this is if you head to water and you're blocked by something. So they actually have something in this code that routes them around barriers. So if they reach water before anticipating it, curiously enough, I think they just try to continue on to the next to the water where they were trying to go to. So they avoid boundaries of the model as well. And then there's periodic vegetation updates according to the model. Okay. Okay. So one interesting thing about this particular model is that it is step-based, so that the agents are periodically woken up based on steps of time, and that's associated with sort of discrete time steps here. And then there's the environment here along those lines. On after step. We'll talk about this in a few minutes. It updates the vegetation. Okay. Just thinking about what to do here. I think we'll take a very brief look at this other model. It's called shelling segregation. Again, it's an example model. So if you go to example models, you should see within example models is a thing called shelling segregation, and I think it's just one of the main ones. Yes, shelling segregation model. What this model is designed to serve as a very simplistic model that can show how segregation patterns of clustering, larger scale clustering of different individuals can emerge out of very modest preferences to live near other people like yourself and the ability to move. So this is an example of a larger scale pattern of clustering between two groups, shown as red and black. Okay, and there's a preference up here to have neighbors of the same color that will motivate an individual to move if their neighbors are below that threshold. They'll have a certain chance of moving. In this case, it may be a certainty. And it's not predefined where these blotches occur, these sort of segregated regions, but the stronger the preferences are, the more movement you'll have. You'll notice if the preference is strong beyond a certain level, it actually can't find it. But this is an example of a sort of pattern that it would emerge there. Now, if we were to pull this all the way, it will just iterate because no one can find a neighborhood that's quite as acceptable. But you'll notice even with with a very smaller amount of preference, it can still lead to segregation. So we're gonna see this. This is an example. It looks a bit like the cellular automata model we saw earlier with Game of Life, but here we have individuals moving, whereas in Game of Life we just had them staying at a certain point. And the individuals here are very simple. They have a single variable called satisfied. Okay. Here we have a discrete environment. So we have a width, and we have a number of columns and rows. In this case, each cell is 4 in width, 4 in height, because there's 400 width, and then 100 cells. Okay. You'll notice you also specify neighborhood type, and this asks how many agents are you connected. A Moore neighborhood is essentially north, south, east, west. A Euclidean is north, northeast, east, southeast, south, etc. Okay, so here what we have is a population of people, and the people here are set randomly to different colors. The colors set randomly at first, and they're associated with the environment. There's 8,000 people. Okay. Now, also associated with this is a threshold, a preference threshold, and the preference threshold is updated by this slider. So this slider that we get when we first run the model goes and it sets the preference level of a given individual. Okay, so it sets the degree. Excuse me. This is during the model execution. I misspoke. It's actually during the model execution that it live updates this thing. So it's in main, and it sets the threshold on an ongoing basis. This action is invoked when you slide the slider. So in this case, the action is just set threshold equal to the current value of the slider. Okay. Okay. So persons are shown as just little dots here, and the color is set, as we saw earlier, to red and black with equal likelihood initially. So they have a color parameter, and then they have a variable that indicates whether they're satisfied. Okay. Their location is set by the environment, and in this case we have a step-by-step model taking place. So they're evolving in a step-by-step basis. It's discrete time, much as was the model that was used for Game of Life. So here what happens is there's a distinction between the step itself and the information gathering before the step. So there's a thing called on-before step that gathers all the information needed to actually make the change. And we separate those two because otherwise, if the information gathering was combined with making the change, it could depend on what order, what change a given agent undertakes could depend on whether or not other agents have updated before it. So instead, we separate these out. All the information is gathered by an agent ahead of time before anyone makes any change. And then all the agents perform their updates. And at that point, it doesn't matter what order they go in, because they already had gathered the information they needed to determine what's going to happen. So here, we have a very simple rule. So within this, for every time step, a person is considered satisfied if they have no neighbors. If they have neighbors, it goes through and it accumulates what? What does this code do? What's the function of this code? So it iterates through the neighbors, calling them A, and it checks what? Well, it checks if their color is the same as your own color. If so, it increments some counter. And then it treats itself as satisfied if the number of neighbors that's of your color that it accumulated is greater than or equal to the threshold, this fractional threshold, 0.75 or whatever, times the number of neighbors. Okay? So if you have a preference, if this game has a preference level of say 75%, and you have 4 neighbors, north, south, east, and west, then you need at least how many neighbors to be satisfied to be of your color? You need at least, what's that? Elementary arithmetic, folks. 75, if you need at least 75% of your neighbors to be your same color to be happy, and you have 4 neighbors, how many neighbors do you need to be your same color? 3. Yeah, you need 3 neighbors. And so you're only satisfied if you have the 3 neighbors. If you're not satisfied, and this is the on-step event, after all this information has been collected, if you're not satisfied, with 30% probability, you jump to a random empty cell. This is a built-in thing. Jump to random empty cell. Okay. Okay. So let's we'll go check this out here. So yeah, the likelihood of movement is 0.3. Okay. That's good. Okay. I'm not modifying this. Okay, so let's just talk about discrete space here. We saw some methods for this, and this will be our closing comments here. So there's a few methods that are valuable here. One is jump to cell. Here you jump to a particular unoccupied cell. It needs to be unoccupied. You can't jump to it if it's already occupied. The other is you can have a move to next cell, which moves the agent into a neighboring cell. And you can specify what direction you want to go as north, south, east, west, northeast, southeast, etc. Okay. So it moves in one of these directions. So you can say move to next cell, and it will just pick among those cells. Or you can jump to random empty cell. In this case, you select and it automatically finds an empty cell for you if it can, and it jumps you to it, okay, within this space. Okay. And then there's some methods like find random empty cell, which returns the row and column of an unoccupied cell, and you can also ask for information about who's at what cell, get the agent next to them, get the neighbors of a given agent. Okay, now the important thing I want to leave you with here is this issue of separation of synchronous mode from asynchronous. In this case, we have a synchronized mode where we go in steps. And the way this is handled is, again, we separate out the collection of the information in on before step from the actual execution of the step, which occurs in on step. Okay. The issue here is that it's difficult to know if 2 agents will collide using data on the current time step. For example, both want to move to the same location. And that's something that it's hard to avoid. If you update asynchronously without this sort of lockstep movement, they're updating at slightly different times. Whichever goes first seizes that, and that's fine. So really this is something that arises for discrete agent movement and that you have to worry about. Right. I will note that we're going to come back to, so I talked about 2 types of embedding, 2 types of mobility. Mobility on the one hand in continuous space, movement that's continuous, people pass each other without colliding, and then a discrete situation where people move to cells. The cell can only be occupied by 0 or 1 person, and commonly people move in lockstep, although not always. In this case, we have a third situation that's shown here, which is irregular spatial embedding. This is making use of what any logic terms network-based modeling. I think a better term for it would be process-centric modeling, and we're going to see this in probably another 2 weeks or so. But basically, what we see here is movement of individuals through an irregular facility. They move on paths through that facility. And I should note, and this is something Darian's already familiar with, but will not be familiar with most of you, another option for moving people within any logic, if you have agents and you say, move in this direction, they can move in continuous space, but you can also say move along a line, or a line, a curve, and it will actually move the agent along the curve to reach a given destination. So it can kind of route it among a network of curves. Within this sort of modeling we see here, that's the technique that's used. Here we don't, these are actually not agents, they're resources or entities within a model, and they move throughout this facility in a continuous fashion. This sort of modeling will be used to examine bottlenecks, for example, bottlenecks associated with rooms to see patients, bottlenecks associated with measurement or testing equipment, bottlenecks associated with checking people into a facility, etc. So we're going to come back to this sort of modeling, which is very process-centric. There's less attention to how people interact directly and more to the cues that are built up, etc. And this is an example that comes with any logic called emergency department. So this other approach, we'll see it's individual-based, but it treats agents as kind of flowing through and being operated on processes which require resources. And it turns out that within agent-based modeling, you can have irregular spatial embeddings, such as movement along networks of roads or what have you, with some additional custom coding by moving them along polylines. So anyway, we've seen here some aspects of mobility, both in continuous space and discrete space. Some of you might find that helpful when it comes to some of your projects. Okay. Okay. So I also announced there's no there's originally a problem set scheduled, but because I was able to put some of the problems from that into the last problem set, the last assignment 2. There's no further problem set due until the 18th, and I've yet to release that. One other issue that means you have a couple weeks now to really work on your projects, okay? I've gotten descriptions of projects from most of you, and I've been going through. I think most of you have gotten back some initial comments from me. I'm going to have office hours right now, and I'd be glad to talk further about any issues. But I'm also glad to create one-on-one appointments or to meet next week. But see if you can use the next few weeks, the next 3 or so weeks until that problem set is done, to really substantively advance your projects. There is a hand-in, I think, on the way. I think it's maybe on the 11th, where I ask you to turn in some more further updates on your projects. So be sure to get started and let me know if you want to meet. Okay? Okay, very good. Thanks.